In this lesson, we're trying to do three things. We're trying to talk about amplitude, period, and wavelength. Let's change colors here. All right, so if we have any kind of a periodic function, such as the ones that we were studying yesterday and that you can find in your book on page 699, each one of them is going to have a certain amplitude. Each one of them is going to have a period or wavelength. And the thing is, wavelength and period are kind of the same thing, and we're going to talk about that in just a second. This is the midline of the wave, or of the disturbance. The amplitude is the distance from the middle to the top, or from the middle to the bottom. You can also find the amplitude by taking the maximum plus the minimum, and maximum minus the minimum and dividing by 2. That would be the amplitude. So, we're going to do some examples in just a few minutes of amplitude. Period is the distance from where a wave is at one time to where the wave is at that exact same spot again. That's the period of the wave. Now, if that period is, if the horizontal axis here is in time, that period will be in seconds or something like that. That same distance is also called the wavelength if that horizontal distance is a length of some kind. Now, I can't think of too many instances in which the horizontal axis is a length. I suppose, like if you were measuring ocean waves, then it would be a wavelength. Or if you were measuring earthquakes, then it would be a wavelength. Let's look at some examples here. I downloaded some stuff from the internet. Let's see here. Got some pictures for you. Okay, here's an example. This is the average yearly temperature in, boy, that's a bad picture, in Chicago. Okay, so what you would have to do, is, if you notice here, they got the months down at the bottom, so this is a time graph. And then this would be the high, this would be the low, and then the average here is the green. This is a periodic function because it starts here and it ends here. And then, of course, it would continue the next year going up again, because you've got from the period is 1 year. Now, they've got the low temperature here is 10. So this is 10, here's 20. Looks like the average at the beginning is about 35. The average in the summer is about 75. So the amplitude, I'm going to change colors. Amplitude would be the high down to the high of the average down to the low, and then divide that by 2. So 75 minus 35 divided by 2. So the average would be 20. I'm sorry, the amplitude would be 20. Now, the midline then is halfway between 35 and 75, which would make it about 55. Here would be the midline of that wave, somewhere in there. Amplitude, period, and then you can't really do wavelength here because I suppose you could. You would just say the wavelength In math, we abbreviate wavelength lambda. That's the Greek letter L. Lambda is 1 year, which isn't really a length, it's a time. So that's why you shouldn't really say wavelength there. Let's look at the next one. Here's a EKG of a person, and you see there's different leads here. There's the, oops, I'm going to get a picture here for you. There's the AV lead, AVR right side, AV left side, AV front, and then you've got the V lead, the T lead, T1, and then V5. Okay, so those are all the different leads that you have. If you notice here, it says the horizontal axis is 25 millimeters per second. So a second would be 5, 10, 15, 20, 25. From here to here is 1 second. And then the vertical distance, oops, I gotta erase that so you can see what it was. 10 millimeters is 1 millivolt. So, let's do that vertical distance also then. So, we would go from here, oops, we would go from here up to here is 1 millivolt. Okay, let's do the period on a on one of the leads that it's pretty periodic. Let's choose this one right here. Oops, this one right here. Okay, so what we're going to do is to find the wavelength. I'm going to abbreviate that lambda. It's shorter. Now, I'm not going to do wavelength because my horizontal axis is a time, not a distance. So instead of wavelength, I'm going to do period. Okay, so how much time is it from here to here? Well, to find that, I'm going to find out how many waves do we have here on this graph. We have one wave to here, 2, 3, 4, 5, 6, 7 waves. So if we want to do the time per wave, so 7 is our denominator, our numerator is how many seconds? Well, from here, so we've got 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 200, 205, about 210, 210 millimeters. Okay, so we know that according to our graph, 25 millimeters is 1 second. So I'm going to erase that 7 for just a second. 210 millimeters is how many seconds then? Let's get out our calculator, cross multiply and divide. So we would take 210 divided by 25 is 8.4 seconds. So we do 8.4 seconds for 7 waves. So let's find out how many waves there are per second. Let's get out our calculator. Oops, calculator. Come on. Waves per second. So 7 divided by 8.4 is so 0.83 waves per second. Let's do it in waves per minute though. So so how many would that be per minute? Multiply that 0.83 times 60 gives us 50 beats per minute. that's what that person's heart is beating at. Now, if you notice, the graph says it's 49 beats per minute, so we were pretty close. We could also find the amplitude of this wave, and they're all pretty much the same. This one looks like the biggest amplitude that I see is from here up to here. So we would take, how far is that? That's 10, 11, 12, 13 millimeters. Well, 10 millimeters is 1 microvolt. So 13 millimeters is 1.3 microvolts, but we have to divide that by 2 because amplitude, remember, is from the middle to the top or from the middle to the bottom. So we get about 6.5 millivolts, not microvolts. And then you could do the same thing for each one of the other graphs. And if you notice, the leads do catch the same heartbeat. They just catch it in different parts of the body, and different strengths happen with each of those parts. Okay, let's look at the next picture. See what do we have. So here's another. Oh, this one's got a good heart rate. Look at that V5 down there. That's really a good strong beat there. Another one. Bunch of EKG pictures here. And in each case, they always use the same scale. You notice they've got 25 millimeters per second on the horizontal axis and then 10 millimeters per second along the other one. Oops, that's a picture my grandson made for his mom. Let's go to, here we go, Pensacola tides. This is a good one. So these are the tides at Pensacola, Florida. This would have been last Saturday. I'm going to make this side bigger so that I can see better. Okay. Get my calculator. Oops, I don't need the calculator right now. I need the picture. Make a picture here. Okay, so let's do, this time again we are better off with period, because if you notice our horizontal axis is distance, our vertical axis is in feet, MLLW, mean something water level. I forget what the W or LL stands for, but it stands for the average height. And if you notice, the average sea level is 0 here, and all of these waves are above average down in Pensacola, which I'm not sure if that's because of the time of year, of the tide, or what it is. But all of these fluctuations are caused by the tide. There's average right there. Remember, average is the middle or the midline of the wave. Okay, so let's figure period. The period from here to here. Well, if you notice, here's 0 o'clock on the 7th. Here's 0 o'clock on the 8th. And these times are local standard time or local daylight time. So it looks like the first high tide, or the first low tide here, was at about 3 a.m. And then the second low tide looks to be about almost either 3:30 or 4 o'clock p.m. 3:30 p.m. So from here to here is 12 hours and 30 minutes. So the period would be 12:30. Okay, and then the amplitude is the amount of high tide over average or low tide over average. So it looks like it goes a little bit above 1 foot. I'm going to say 1.1 feet minus the low here is about 0.2 below, so minus negative 0.2, and then divide that by 2, and you get the amplitude is 0.65 feet. So there we've got period, and we've got wavelength. Let's look at the next one. That's the Chicago temperature again. Here's another, this is in Mississippi, its wavelength and its period. You can see that the high tide is a little bit later there because it's a little bit farther west. Here's a good one. Here's the water temperature in the Bayland Yacht Club. So let's do that one. So it's kind of not as clear a periodic graph, but if you notice, here's the low, here's the next low, and in both cases the low is at a little bit right around 1200, but that's Greenwich Mean Time, which would be about 6 a.m. in Mississippi, maybe 7 a.m. I guess that's closer to 7 a.m. in Mississippi because Mississippi is in Central Time. Okay, so you got the period is 24 hours now, right? From 12 a.m. till 12 a.m. on the 8th. And then the amplitude is the high, which looks to be about 50. Well, for this wave, the high is 56. Minus the low looks like about 53.8 divided by 2. So we have 56 minus 53.8 divided by 2, and we get about 1.1. And then the midline would be halfway between those two. Looks to be about 55 degrees, right around there. Okay, so that's how you do this assignment.